through that. Okay, so I divided the lectures, the three of them, into northern hemispheric reconstructions, so global reconstructions, and spatial or local reconstructions. And I said that I believe that the first one is significantly easier as compared to doing an entire reconstruction in space and time, not just only in time. So with the northern hemispheric reconstruction, I went through the hockey stick approach, the uncertainty quantification approach, and the robust reconstruction approach that we did. And I started looking at the expectation maximization approach and the kind of problems that we run into when we try and do an entire local reconstruction or spatial reconstruction. Right? And if you remember this picture, we were reasonably successful in doing a robust reconstruction in the sense that we were able to get the uncertainty down, and this model had many moving parts, including different types of optimization that was required, the statistical model that was there, autocorrelation, and how to measure uncertainty. So, however, that endeavor seemed to have been worthwhile because we seem to have gotten the uncertainty down and gotten a reasonably good reconstruction. But when you go to a spatial one, this is what I started talking about last time, which is the REGIEM approach, we ran into all kinds of problems. And I'll quickly recap what the REGIEM approach is because I need it for today's talk too, and also just as for the purposes of recapping. What we were trying to do was we assumed that temperature and proxy, every year, right, the rows represent years, were distributed normally with a certain mean and covariance matrix. And we have data during this part and this part, not fully, but somewhat going back in time. And we were trying to look at the relationships between the proxies and the temperatures so that we could infer missing temperature. The big problem that we encountered was that in every single row there could be missing values. So what do we do? Right? So like here's an example. Right? We have temperature going back all the way back at a given location, but proxies, well, there are missing values. How do we do that? How do we overcome this? Because if we were to do a regression of temperature on proxies, and if there are missing values, even just one of the predictors have a missing value, we can no longer use it for regression. So how do we overcome that? Especially because data is very precious here. We want to use as much of it as possible. And the REGIEM approach that was proposed by Schneider, which in fact is based on the expectation maximization algorithm, tries to do that. So what we do is we divide each row of that data matrix here into a missing and available part, right? And we subdivide that component into its respective parameters, right? This is all it is a random vector, and I'm subdividing it, and it has its own distribution, each of these components. And then you can regress the missing on the available, so therefore you can impute the missing on the available and fill out all the rows. So once you have a complete data set, I'm able to work out the mean and the covariance of the field and go back and forth. That was the expectation maximization algorithm. There's a rich body of theory around this approach, and it can be shown to converge, right? It's widely used, right, in many fields now, and it was proposed by Dempsey, Leighton, Rubin. And the illustration of the EM algorithm is given here, where we start off with an initial parameter value for the mean and the covariance, right? From the covariance, we need these parameters, sigma AA inverse and sigma AM. And as Michael pointed out, rightly so last time, this inversion is a problem. It's a very good point, and I would say one of the most important points is that if you don't have enough data and you have a huge spatial field, the number of available spatial points may be in the thousands, but you only have 150 years of data. It's dead from the word get-go to try and invert it. It's rank deficient in a very serious way. So how does one overcome that? However, remember that the ill-posed part of the problem comes from the covariance matrix. It is, if we have a spatial field of 5 by 5 degrees latitude and longitude grid boxes, that's about 2,000 points. And so we have a huge covariance matrix, and 2,000 choose 2 parameters in the million correlations to estimate. We only have 150 data points. What do we do? Right? This is a huge matrix, right? And to overcome this problem, overcome this regression problem, essentially it's a multiple linear regression of the missing values on the available, right? So really regress one component of this vector xm on xa. It happens to be, instead of a linear regression with one response variables and many predictors, but rather a number of response variables and a number of predictors. It's just a multiple linear regression, and it can be derived just by looking at it as a conditional normal distribution, the distribution of m given a, because we know with the multivariate Gaussian distribution what the conditional distributions are, what the marginal distributions are, and so forth, and we can just get to this relationship very easily. It's just a regression of the missing on the available, right? So by doing this, we're able to impute the missing values, the entire field, go back and forth, and eventually the algorithm converges. We have a completed field which will allow us to complete this part, the missing temperature, in a statistically credible way. So we can say we've used the wealth of the entire data set that we have without throwing anything away, and still have an imputed, right, climate field for the entire globe going back in time, spatially, because of this. So it's, in a very real sense, it's a very usable and rich methodology. The problem that comes in is that this inversion that's required, and that's ill-posed. And several methods have been proposed to overcome that, including principal components regressions, truncated total least squares. This is a very, I would say, highly used method. All it really is in order to do the...
Can you say in 2 words why you said this is considered to be the gold standard as opposed to some of the other ones? Can you say what the advantages are?
Sure, of course, of course. With the, so in terms of regularization, people have either used ridge regression, principal components, or truncated total least squares. They are not very different, principal components and truncated total least squares. There's just been a general preference because a few have used truncated total least squares. And the form of the optimization procedure that leads to truncated total least squares also assumes that the matrix A here could be perturbed to solve this linear system. That's the reason. So it's slightly more general than a least squares regression. And ridge regression, all they really do is to take the covariance matrix and add an element of the identity, a constant of the identity to it. Yes, go ahead.
Is there an assumption that the regressions are stationary in time as you go?
Yes, I mentioned that yesterday. It's an unrealistic assumption.
So for example, if I, in a simple example, if I know the temperature in the North Atlantic and I want to calculate the temperature in the South Atlantic, I'm assuming that there's some correlation now between them, but the connection between them could be completely different, 20,000 years ago.
Yes, yes. And can you imagine, we have a 2000 by 2000 correlation matrix, which we assume with 150 years of data. If you want to get another regime, a covariance regime, at a different point in time, we have another 2000 by 2000 covariance matrix. And I would say good luck with that. So it's true.
You seem to refer rather to invariance in space.
No, in time.
So,
You're calculating correlations now, and you're applying them to the past, right?
so we assume that the mu... Yeah.
That was an example of a special correlation.
Yeah, so we assume that mu and sigma stays constant over time. They're independently and identically distributed. Firstly, they don't have to be Gaussian. We can relax that. Schneider doesn't, but we can relax that. In some sense, assuming they are independently distributed over time, well, I don't think that's true. There's autocorrelations. Are they identically distributed? That's a completely different probabilistic assumption, right? They could be independent identity, where your mu and sigma over time could be different. So all these assumptions can be pulled apart by a probabilist or a statistician. And as soon as you start pulling them apart, you need more data, right? And there are ways to overcome this, and hopefully I'll try and convince you. Here's one approach to try and do it a little bit better. Right? And, but it's a very good question. I'm glad you asked, because this is a problem. We assume that the covariance structure and the mean structure doesn't change, and it's very unrealistic. So it's a good point. So let's then, what I did was I just said, well, what were these ridge regressions, principal components, and truncated total least squares? They really referred to a singular value decomposition, or trying to solve a linear system using a few principal components or few singular values. That's what it was. And when we do this regularization, the whole purpose behind this regularization is to solve an ill-posed problem. It provides a unique solution to a problem with multiple solutions, provides us a solution with good properties, right? Of course, choosing the regularization parameter is not so clear. If you regularize too much, that means your fidelity to the data is you're moving away. At the same time, if you don't regularize enough, then it's unstable and it's ill-posed. And this is a very well-known phenomenon in applied mathematics, right? So in order to illustrate how this technique was doing, we tested it on a test bed, which was these so-called pseudo-proxy experiments. And these pseudo-proxy experiments really are, right, general circulation model data in space and in time. And that is noises added to them. And after noises added to them, we try and reconstruct the climate from a reconstruction method, just like the RegEM approach. So this is what I went through yesterday, and we can compare it, right, in terms of what is the mean squared error compared to the truth over time, and what's also the coefficient of efficiency. Is like saying, well, you've done a reconstruction of the past. Is it better than just using the mean? And that was what the coefficient of efficiency was. And I covered all of this last time, but I'm just want. And then we did a reconstruction, right? Spatial reconstruction, right? For the RegEM, the TTLS method, the RegEM TTLS method, right? Going back all the way up to 800 AD. And the black curve is the target. The red curve is the TTLS. It seems to do pretty well, right? In terms of getting the general movement, right? But this is an aggregation of what we have done spatially, right, in time. And what we were interested in doing, was doing it spatially, not just an aggregate northern hemispheric or global temperature. But when we went down to look at what was happening in space, and the coefficient of efficiency was one way to measure whether it was good or not. Anything above 0 is good, anything below 0 means that we may as well just use the mean, not the proxies. And in that case, it became pretty apparent that it wasn't doing very well. It was doing quite okay in North America, where there were proxies, and in Europe. And besides that, it wasn't very good. And that was concerning. And when we undertook a local reconstruction over North America and Europe, it became pretty clear that certain regions were not good at all, like the Great Lakes region, and over the United Kingdom, and for example, and over of Russia and the Greater Caucasus regions. So there was a problem with the RegEM method. So how do we overcome this? So in this, the last lecture of the three, I thought I'll propose a new method we've come up with recently to try and overcome this. Well, if you remember, estimating the covariance matrix was a big problem, right? And so inverting it was a big problem. We have very little data. How do we estimate the covariance matrix properly? And also, this is estimating covariance matrices, especially in a sample deficient, or what is often referred to now in statistics as a sample starved setting, is a challenging problem because of the limitation of the sample sizes, right? So how do we go about doing this properly? The standard covariance estimator, which is the sample covariance matrix estimator, it's just, not only is it rank deficient, it's a poor estimator of the true covariance matrix. You need samples like, at least, I would say, if you have a sample of, if you have a 2,000 by 2,000, I mean, you need into the tens of thousands of data points before you can get even an accurate estimate of the covariance matrix. Unless there is some underlying structure that we can exploit. And is there some underlying structure here in a spatial field that we're not exploiting? That's the first question that we asked. Is there something that's happening that we're not taking advantage of? In other words, we're asking, we are trying to get a covariance model as to how temperature at different points in space are related. However, is this relationship, can we project it to a lower dimensional space? I mean, and that's a natural question. Yes, Ruben, yeah. Go ahead.
Shouldn't you exploit the density of the observations and just not try it where there are no observations?
Yes, so one approach that we do is only to try and do a local reconstruction where there is more data. And we certainly do that. That makes sense. So in other words, throw up your hands up in the air and say, I give up trying to do it all over the globe. It's not going to work. I don't have data. So let me just do it for regions where I have more data. Because it makes a lot of sense, mainly because these proxies are reflective of local climate. So it may make more sense to do it where we have data. However, there are some questions one tends to ask where there isn't as much data. For example, in parts of the equatorial Pacific, you may be interested in the El Nino-La Nina effect, and we don't have tree ring data. We have some coral data. It may not be sufficient. It's often not sufficient. How do we still reconstruct the climate there? Or in the poles, where we have very little data. We have some ice core data, but it's not sufficient. We're still interested in those places where there isn't as much data. Can we borrow strength using a spatial model? So that's a question, right? And so how do we estimate these covariance matrix really is a big problem which is embedded in this paleoclimate reconstruction problem. If you go back to the REGIEM approach, as I said, what is really the issue here? It's estimating the covariance matrix. And doing the sample covariance matrix is just not going to work. So can we somehow do better? So that's the question that we asked here. And what most people do is they take the covariance matrix S and add a ridge type penalty. In other words, a constant multiple of the identity, so it's invertible. And it's usually, it has some good properties. It corresponds, it has a Bayesian interpretation and so forth, right? And it's interpreted as some kind of ridge type penalty. So that's one approach that has been found to be useful. However, when we try and use it in pseudo-proxy experiments, it's not satisfactory, I would say. Another approach that's been used is to model the covariance structure. Instead of saying I have a 2000 by 2000 covariance structure matrix to estimate, an approach that some have proposed is, why don't I get a covariance function which models models the spatial relationships over space? And that was proposed by Hybers, for example. The problem with that approach, in the way we see it, is that it does not respect land-ocean boundaries. Right? The correlation stays constant whether it just only depends on the separation between 2 points. But if the points go between land and ocean, then the correlation may differ. So even though it's a very good approach, right, it was proposed by Tingley and Hybers, is that, and that's one way to make sure that you only have a few parameters to estimate, to have just a covariance function, and it has a few 3 or 4 parameters. It may not make as much sense from a geosciences point of view, because just the correlation is not only a function of the distance between 2 points. It's their specific locations will matter, right? And the correlations between 2 points in the ocean will be very different from 2 points in the land, let alone one being in land and one in the ocean. So until it's not a flexible enough model, that's what we have seen. So it's a good model, but it's not as flexible that respects the topographic features that we are often faced with. On the other hand, estimating the full covariance matrix is very flexible, but we don't have data for that. So do we have a middle ground situation? I mean, if you have kind of like a covariance function, all it really says is, I mean, those of us who have done, who are familiar with these positive definite functions, all they are really are isomorphisms to positive definite functions. And you can, in fact, have ways of just representing the relationship between 2 points in space, right, using these functions. And the exponential function just has, and the Matern have 3 parameters or 2 parameters. So it's really a good model in that sense, except that it is restrictive, right? So can we find like a middle ground situation? For example, what I meant by that is land-ocean boundaries, mountain ranges, and there are teleconnections too. And we want a model that's flexible. But if it has too many parameters, we can't estimate it well. We can't estimate the parameters well because we are in a sample deficient setting, right? We have a 2000 by 2000 correlation matrix. That's not good enough. A function that is able to represent those correlations in a more simpler functional form, like the Matin covariance function, is just not good enough. It's too restrictive, not too flexible. So how do we overcome that? Well, we need a flexible spatial model with just a few parameters to estimate, but it must also make sense from an earth sciences perspective, not just from a mathematics perspective, right? So we need the right balance between flexibility, complexity, and scientific credibility. So this is a very tall order in some sense. So how do we overcome that? So here's something that we've proposed very recently, right? So recall first that our goal here, our pursuit here, is to try and see, is there some structure that we can exploit to try and do the covariance modeling better? First, remember that if you have a standard normal distribution, can we put zeros in the covariance matrix and reduce the parameter space adequately? That's a natural question to ask. Because you have 2,000 choose 2, right, in this million parameters. Can we put zeros in the covariance matrix? In other words, induce sparsity in the covariance matrix and estimate only a few parameters very well, right? And we know from very standard statistics that if a covariance, which is nothing other than a correlation, right, which is not standardized, if it is zero, a correlation between two random variables is zero, means that that component xi and xj are independent. And it's a very basic concept that you learn in statistics, right? So one would wonder, well, can we put zeros in the covariance matrix or the correlation matrix to try and reduce dimensionality? Well, it doesn't make sense. And the reason why it doesn't make sense is because even further out in space, there is still a correlation between 2 points in terms of temperature. The temperature, for example, let's say in Mexico City and where else?
Austin, Texas.
Buenos Aires, okay, right? It won't be zero. It may be very close to zero, but there are still some relationships. So the correlation is not always going to be zero. You can't always assume that it's going to, I mean, the correlation does decrease in space, but it does not get to zero. A lesser known property is zeros in the inverse covariance matrix. You take this 2000 by 2000 covariance matrix and you invert it. If there's a zero in the ijth entry, it means xi is independent of xj given the others. So I'm sure this is a relatively less known concept. However, it makes much more sense for the following reason, right? If you have a point, right, that you're interested in, and another point, and you want to understand the correlation, even though the correlation may be non-zero, if the variability of the temperature in that point, who do you think will be able to explain the variability the best? Is it its neighbors, neighboring spatial points, or somebody as point as far as Boston or San Francisco? It's mainly the neighbors, right? So what this essentially says is that if you can somehow say that if you have two spatial points, we can somehow find zeros in the inverse covariance matrix and make sure that it makes sense from an earth science point of view. And I'll try and explain that in the next few slides, because it's a very important topic, important concept. So here's a covariance matrix.
Can I
Yeah, go.
suggest, I mean, there is another way of saying this, that if you truncate, I mean, you know, we've tried to do this in data simulation and so on, years and years ago. If you truncate away from the diagonal, in spite of the fact that the entries of the covariance matrix might be very small, if you just set them to zero, you lose positive definiteness. That's really the difficulty.
So you lose, he said something that is fundamental. You lose positive definiteness if you put zeros in there. Okay, I hope all of you have heard that. You lose positive definiteness if you lose. It's a very important point, and I'm glad you raised it because I'm going to attend to that problem. So here is a covariance matrix, which is a 6 by 6 covariance matrix, right? And here is another covariance matrix which has zeros in it, right? The zeros imply marginal independencies if you have a Gaussian distribution. Of course, it does not imply marginal independencies if you do not have a Gaussian distribution. It means that just your linear relationship is zero, right? You have linear dependencies. This achieves parameter reduction, but as I said, it's not realistic as from an earth sciences perspective, in the sense that even though correlations do die away in space, it's not clear whether you can put zeros immediately and how far out, right, should you put zeros. And secondly, as Michael pointed out, as you put zeros, you may lose positive definiteness, and often you do. That's a problem, because we need to be able to, we were stuck with the covariance matrix which had eigenvalues 0 or higher. If you put zeros artificially, your eigenvalues may slip into the negative part of the real line. That's even worse of a problem, and that does happen. So one has to be careful. But now let me go to the inverse of the covariance matrix, right? When you have inverse of the covariance matrix, there are zeros in the inverse of the covariance matrix. Here's an example, a 6 by 6 matrix. You could think of it as temperature at different points in space and the relationship between the temperature, let's say between Boston and San Francisco, for example, right? Just the relationship. We have to model it. But if you have zeros in the inverse covariance matrix, right, does not necessarily mean that you'll have zeros in the covariance matrix. Right? So the good thing is we want somehow, I'll try and convince you that zeros in the inverse covariance matrix is good to have and makes a lot of sense from an earth sciences perspective. A sparse omega does not imply a sparse sigma. And correlation between faraway points is still possible, teleconnections is still possible with not having zeros in the correlation matrix, but you could still have zeros in the inverse covariance matrix. And what happens with this inverse covariance matrix when we put zeros in there is that we've achieved parameter reduction. We have only a few, this is a symmetric matrix hopefully, and I'm just being presumptuous in assuming that, but it is, right? But if we have lots of zeros, that's good because I only have to estimate a few parameters. Now can I exploit this approach, and why should it be realistic? So what do I mean by zeros in sigma or in omega? So as I said, zeros in sigma, the covariance matrix, means marginal independencies, right? And I said marginal independency is not very realistic. Conditional independencies, right, which are zeros in the inverse covariance matrix, is more realistic, because if I have 0 in the ijth entry of the inverse covariance matrix, omega, it just means that spatial location and another spatial locations are independent given the rest, right? So here's an example from the former Yugoslavia. This is Bratislava, and this is another town. Of course, you'd expect there to be a correlation between the two temperatures, right, in the 2 points. Now let me do the following. Let me look at the correlation between these 2 points after explaining the variability of the temperature by its neighboring points. So what does a correlation do? It really looks at the strength of a linear relationship between two random variables. What if I first look at the linear relationship between these 2 points after accounting for the variability of this one given these? In other words, first I explain the temperature by the neighboring points, and then try and see if there's anything left that this can explain. In other words, I'm just looking at, so what is a linear relationship? I mean, essentially what you're really doing here when you do a correlation is to try and explain the variability in one variable using the other. I mean, that's what a regression does. Can you reduce the variability? Here, what I'm saying is that the variability, right, in this temperature is better explained by the neighbors, and very little is left to explain by this point once you use the neighbors. And what that really means is that if you only look at the correlations between a point and its neighbors, you can ignore the correlation far out. Right? And that really means that in the inverse covariance matrix, you can put a lot of zeros. Right? And this is often represented by graphs. So you may have heard the word Markov random fields or graphical models in this topic. So consider a random vector x1, x2, x3 of dimension 3. I represent them using a network, a graph, right? And when I have a graph like this, 2 and 3 are not connected. It just means that x2 and x3 are independent given x1. That's when x2 is independent of x3 given x1. So this location is independent of x3 given x1. However, marginally they will be correlated, but given a bunch of neighbors, they will be independent. So if we can find out who the neighbors are of each point, right? So in the inverse covariance matrix, besides those points which are neighbors, you can put zeros in those entries. Now what would we have achieved? We would have achieved tremendous parameter reduction in the inverse covariance matrix, because all those all those, what those elements or represent are the correlations, right? Partial correlations that are able to explain the variability of one of these points, right? And this is called the local Markov property, and this entire class of models are called Markov random field or graphical models, right? So, and one uses networks and graphs to represent the spatial relationships, right? Here, for example, xi and xj are independent given these two, and these are called the separating sets in a graph. Now, my main point that I wanted to explain was that you could put zeros in the inverse covariance matrix and make sense from a geosciences perspective, make sense from a probabilistic perspective, and make sense from a statistical perspective, because you have fewer parameters to estimate given your limited sample sizes, right? So a question that one would ask is, well, how do we go and put zeros in the inverse covariance matrix? It's not clear, right? And this is a big area of research, right? As I said, conditional independence relations, zeros in omega, means dimension reduction. The best way that I've seen, in recent years, right, is to do a regularized likelihood approach. In other words, you maximize the likelihood, Gaussian likelihood, just maximum likelihood estimation that you would do, but you're unable to maximize it because it's an ill-defined problem. The answer lies on the closure of the cone, is the problem. So what you would do is you would put an L1 penalty which induces sparsity in the inverse covariance matrix. And you may have heard the word L1 penalty. There are many people who have worked on this, including Ingrid Dobschich, Terry Tao, David Donahoe, Emmanuel Candes, a lot of my colleagues, and so forth, right? Mainly in harmonic analysis and in functional analysis and so forth, right? What are the properties of such estimators? Right? When you put an L1 penalty, what we are really doing is, this is sometimes referred to as the lasso. I don't know how many of you have heard the word lasso. Have you heard the word lasso? Yeah, so some of you have heard the lasso. Okay, lasso means that it's a way to put an L1 penalty to a likelihood, and that induces zeros in the parameter of interest, right? Lasso regression and so forth, right? So this is the problem that we're trying to solve. We put zeros in the inverse through an L1 penalty. Now this rho is often called a tuning parameter. If it's too high, if you put too much of a penalty, it will put many things to zero. You don't want that. You only want those ones which you think should be zero, which the data indicates should be zero, and everyone else not to be zero, right? And this is quite a difficult problem to solve, because for various reasons, right? As I said, adding an L1 penalty favors sparse estimates for the inverse covariance matrix. The higher the penalty implies more sparsity, right? And sparse estimates are useful for achieving the necessary dimension reduction that we need, because there's structure. And what I've been trying to say is there's structure in a spatial field, that the relationship between points are mainly local, and local points can explain the temperature of a point much better than points far away. Even though if you look at them marginally from a bivariate point of view, things seem related, but in another basis, there is sparsity. And this basis is the inverse covariance matrix basis. That's all I've been trying to say. So we're really considering a different version of the problem, which allows us to exploit structure, right? These are called Gaussian graphical models, right? Solving this problem is a convex optimization problem. And the solution is not available in closed form. Various methods have been proposed for numerically solving the optimization problem. So we need to solve it very fast. Why do we need to solve it very fast? Not only do we need to estimate it once to try and do a reconstruction, if you want to do uncertainty quantification because of the bootstrap or something, you have to resample and you have to estimate it again. It's tremendous. I mean, it's a very difficult problem from a computational point of view too. And it's an important research area in statistics and applied mathematics and related problems in pure mathematics. The kind of questions that we ask is, well, when one proposes methods like the proximal gradient methods that Nesterov and others have proposed, right? The mathematicians and applied mathematicians have proposed, do they converge? Is the rate of convergence geometric, or is it linear? And the kind of questions that one asks, right? All kinds of problems. Different people from the statistics, the machine learning literature, and the applied math literature have proposed solutions to this. The machine learning community is very active in this. right? And everybody says they have the fastest method. Like I have the fastest method, everyone says that. Now everyone claims that they have the fastest method, so it's not clear which is the fastest method, right? So we also have got involved in this and proposed a method for it. So let me try and explain what, in a nutshell, what it really does is that if you look at the globe, right? If you choose a certain sparsity parameter here, what it really does is that at different points on the globe, it says who the temperature neighbors are of each point. You only need to really have these points, right, in blue, non-zero in the inverse covariance matrix. So let me take, for example, this point, which is near San Francisco, right? There are only 4 points there which are related to it. So the row in the covariance matrix, which corresponds to San Francisco, you only have 4 non-zero elements, and everybody else, the remaining 1,800 or 2,000 points, are zero. You've achieved tremendous parameter reduction, right? And of course, this network is often represented graphically. Okay, and you could do, as you decrease the parameter, the penalty parameter, sparsity is lost, and you have more neighbors, as you can see. It depends on the level of regularization that you put in, the penalty that you put in, which what it really does is it takes small elements and puts it to zero. That's all it really does, in a principled way, in the inverse covariance matrix, so that you've achieved zeros in the inverse covariance matrix. And as you increase decrease the penalty parameter, your sparsity is lost more, and you get lots of, right, spurious relationships that come through. So the question is, what is the right penalty to put in, right? Another alternative method is just, instead of doing this, solving this problem, right, maximizing this log likelihood or penalized log likelihood, we could also do something else. We could say, I don't want to maximize a function. I want to take each point in the inverse covariance matrix and just get neighborhoods, right, around them, like what we have done here. The advantage is that it provides a reasonable graphical structure for the data, but you need to choose radius for the neighborhoods, and it's not as flexible, and you could lose teleconnections. For example, sometimes the temperatures in North America are known to be related to what happens in the equatorial Pacific. So if you just only look at temperatures in certain regions only explained by the neighbors, you may lose some geosciences interpretation. So we need something more flexible, whereas the first approach only puts those covariances, or what I would say inverse covariances, sometimes referred to as partial correlations, to zero if the data indicates it. And still you get a good solution in terms of only estimating just a few parameters and doing so well. Why? Because there is very basic structure in a spatial field, which is that you are mostly often related, your temperature is best explained by neighbors, or at least the vast majority of the variance of temperature is explained by neighbors. So we should be able to regularize using this information. Yes, Eugenia, go ahead.
Sorry, I wasn't sure whether you were computing or just assuming that the neighborhood.
Oh, this is just to illustrate the fact that if you have a 20,000. We have checked it, and this method is not so bad. It's actually pretty good also. But the previous method here is more flexible. This one here is more flexible, yeah. So
how do you check that? So you just put the additional constraint on sparsity?
You mean how do I check, how do I put a neighborhood like this, you mean? Yeah.
Put the sparsity constraint, like in which row, which column, like you say, sparsity.
Yeah, so we have an omega. So here is a temperature location. Let me take New York, for example, and I have a 2,000 kilometer neighborhood around it. So we'll immediately put in the adjacency matrix. You could do some kind of Hadamard product or something, it doesn't matter, where you have an adjacency matrix where for each temperature location you have ones for those neighbors and zeros for non-neighbors.
Okay, so the number of these neighbors,
how do we choose the neighborhood locations? There are 2 or 3 different ways of doing it. One of them is in a pseudo-proxy experiment. You can choose it out of sample or by cross-validation. It's computationally intensive. That's one of the reasons. Often what we have discovered is that if you choose something like a 2,000 kilometer neighborhood, you may get a few more non-zeros than you need, but it is sufficient to describe most of the variability. So it's pretty robust. So that problem, obviously, as long as it's not too tight, the neighborhood, and not too If it's too tight, that means there may be other neighbors, right? 2-step neighbors, 3-step neighbors who are also who are able to explain the variance of 1 point temperature better, and we are losing out on that information. You wouldn't want that, or you wouldn't want to sort of like then take a much larger neighborhood, and then you'd have to estimate so many parameters. If there's some reasonably satisfactory balance between these two competing objectives, it's pretty robust, at least from practice. But a principal way to choose a neighborhood is, of course, through cross-validation. Right? Okay. So now that I've estimated the zeros in the inverse covariance matrix, I'm back to my problem. I'm able to overcome what I would consider as the most important problem, is the covariance estimation problem here, right? So once I have that, I'm able to estimate the covariance matrix better. So I go back to the reg-EM approach. I have a structured covariance matrix, right? From that covariance matrix, I can work out these coefficients which I need. Remember, I need to invert sigma A. I'm able to invert it much better now, with no problem at all, right? And I go back and forth. Now, all I'm really dealing with now is I'm estimating my mu and sigma, imputing the missing values, right? I have a completed data set. Then I again calculate the mu and sigma, but enforce structure in the sigma because there are zeros in the inverse covariance matrix, and I go back and forth. And it's
Don't you call that official information matrix?
which one here?
The inverse covariance matrix.
The inverse covariance of the inverse of the log likelihood, yes. Yeah, this is just the inverse covariance matrix, yeah. Right? So here, so that's one way of doing it. It's a principled way because it's really based on maximum likelihood estimation, which is a well understood technique, well studied techniques, including what he said, Fisher information. It attains the Cramer-Rao lower bounds, and it's asymptotically efficient and consistent, and all good properties that a mathematical statistician would care about. So it's based on that. However, it is computationally intensive because running each of these convex optimization problems takes time. That's why there's lots of optimization efforts that have been put into this area. But sometimes you may not want to do a reconstruction at a 5x5 degree grid level. You may want to do it at 2x2 degree or even more finer, at a finer resolution. That's a problem. And these approaches break down, after like dimension 3,000, 5,000. It's not very. It takes forever to do it. And if you don't want to do it just once, you want to do it many times because of bootstrapping, and even more because of cross-validation. So you need superclusters to run these, and that's a problem. Another question that you may ask is, well, I want to put zeros in the covariance matrix. Is there another way to do it, which is just, let me put zeros. Let me ask the question, will this matrix resulting thresholded matrix, right? What am I really doing? Thresholding elements to zero. Will it be positive definite? And Michael said he ran into that problem, and so has other people. How do we think about that? Well, what we studied is that we've taken sample covariance matrices and hard thresholded them. Means that whenever an element is small, below a certain level epsilon, we put it to zero. Okay? Or we can do what's called soft thresholding, which is a certain function, which looks like, I'll explain it later. And general thresholding, what you really do is we look at functions. You take a covariance matrix. Can I find a function which I apply to it such that it will remain positive definite? In other words, you apply the function to the off-diagonal elements to see if it remains positive definite. What I mean is I take a positive definite matrix, I apply functions element-wise. Will it remain positive definite? This zero is not a standard linear order that you get on the real line. It's the Lerner ordering. It's a partial ordering, the Lerner ordering, right? I know if you're a pure mathematician, I think that will be pretty clear to know what I'm trying to say, right? I think you know what I mean, right? It's a partial, it's the Lerner ordering. This is a much more difficult problem, and similar questions have been studied by pure mathematicians, Schoenberg and Rudin and others in the past, from Princeton, I think, right? And it requires techniques from analysis, harmonic analysis. And
that's the Schoenberg of cardinal splines?
Yeah. I can't pronounce his name, but anyway. You got it. So we also look at ways to do this. So what do I really mean is, here is a correlation matrix. Can I apply a function to it and to improve its properties? In other words, become better conditioned, positive definite, and sparse, right? So typical examples in statistics is that you put, if a correlation is greater than or equal to epsilon, you leave it as it is, otherwise you put it to 0. And soft thresholding is that you continually bring it down to 0. And this is the so-called L1 penalty, lasso penalty, right? And some of you may have seen that, right? So the question that was, what kind of functions preserve positive definiteness? Because it's much easier to do this because we don't have to do optimization as compared to taking a likelihood function and putting an L1 convex penalty and maximizing it. That's a difficult problem, right? And it's an optimization. This is not an optimization problem. You just have to just knock down small ones to 0, and then you have a covariance matrix, a sparse one, which of course is going to be well conditioned often. Is it positive definite? Well, this was, of course, looked at first in the pure mathematics literature, right, by Schoenberg and Rudin and others, who says, if you take a matrix, a correlation matrix, and apply functions to it, both to the diagonal and to the off diagonals, you apply it everywhere. We are not interested in applying it to the off diagonals. We don't want to touch the variances. We just only want to put correlations to 0. It's positive definite is equivalent to the function being analytic and having non-negative Taylor coefficients, being absolutely monotonic. So this was proved in a Duke Journal of Mathematics paper and the introduction of the American Mathematical Society paper in 1942 and 1959 by Schoenberg and Rudin. Right? These results are good, but in statistics it's more natural to apply a thresholding function only to the off-diagonal elements, to leave the variance terms untouched. So Schoenberg and Rudin's results are not applied directly. So in a very recent paper, also in the transaction of the American Mathematical Society, we extend their work and we show that the kind of functions which can preserve positive definiteness. It's a very important question because then we know we have theoretical safeguards that I have a quantity which will be a positive definite, which will be sparse, and I can use it, which is that these functions have to be analytic, bounded analytic, and absolutely monotonic. Right? So that means these functions have to be of a certain class of functions. And I won't go into detail except to say that there is some interesting, not only applied math and stats problems, but very difficult problems in pure mathematics too. And if you're interested, I'd be happy to talk to you about it. But now let's go back to the real problem. How does my sparse covariance modeling work? I mean, is it good? Does it give better results? We go back to our pseudo-proxy experiment setup and try and compare it to truncated total least squares. And this picture looks at the improvement in mean square error between truncated total least squares and our Gaussian graphical model, the graphical model, right? And we plotted it spatially. As you can see, anything which is positive, where there's improvement, is either white or red, and blue is where it's negative. I mean, for the most part, these gains are uniform in space, are much better, as you can see, right? Except for some parts here, parts in the a part of the lower Pacific and in the Indian Ocean, you can pretty see that the gains are much better than the truncated total least square. So by exploiting sparsity, we really are able to do a much better spatial reconstruction. And we also do it in North America, and you can see we can reduce the uncertainty bands quite a bit, where the red is truncated total least squares and the blue bands are these sparse inverse covariance modeling approaches. Okay? And do you remember yesterday and today I showed truncated total least squares for North America, and I said the Great Lakes region was not, we didn't do much better than just using the mean, and just compared to using the proxies. Well, we fixed it when we used these Gaussian graphical models. Right? It's much better. So same thing in Europe. Remember, over this region it wasn't very good. We're able to do better. So in other words, by projecting the problem into a lower dimensional problem, we're able to exploit the natural structure and model the relationship between proxies and temperature much, much better. And the question that you may ask is, well, you have an inverse covariance matrix. In reality, how many points are they related to, right? Now, this was a field with about almost 2,000 points, okay? And this picture tells you how many points each of these points are related to. So, for example, this point is blue. That means there are 50 neighbors. So in a row, you may have a 2,000 by 2,000 row matrix, but only 50 of those are non-zero. They have neighbors. So we've really achieved tremendous parameter reduction, right? And in a data adaptive way, and that's what we've done here. And as you can see, except for a few points which are red, where there are about 100 neighbors, even then it's better than modeling 2,000 correlations per row. So it's pretty good. And this is the distribution of the number of temperature neighbors, and this is the degree percentage, right? So on average, the degree percentage is just 3% in the graph, right? You could have as easily as much as 2,000 neighbors. On average, only 3% of those number of neighbors. That means you've achieved almost 97% parameter reduction, and that's just fantastic. And obviously, there is rich structure in these spatial fields, and we've tried to take advantage of that. So we've also done a real reconstruction using coral proxies, right, at 32 temperature grid points. This was data that Julien gave to us, and we acknowledge those who gave us the data, right, his collaborators, and 32 temperature grid points, and 58 proxies in North America. And you can clearly see here that the uptick that you see here is well beneath the bootstrap, even for a local reconstruction like North America, where, of course, as Eugenia pointed out, one should do it where there is data. And we've done it in North America where there's data, and the uncertainty bands are also lower. There's more to this, and I won't go into it in detail because there's more statistics to explain. But just to say that there's lots of scope and potential to for using these sparse graphical models or thresholded covariance or correlation matrices for modeling the spatial structure. So if you're interested in spatial structure, right, spatial reconstructions, how climates of the past were, for example, in Latin America, we can do it. We have not done it here. We've done it globally, right? But we can in fact do it also for Latin America, and get reasonable estimates, provided there is some proxy data there. Right? Of course, it's much easier to do for both North America and Europe just because of the data that's available. So I think I'm going to stop and see if you have questions, and just say that these Markov random fields provide a flexible covariance model. It's not over-parameterized as compared to when using a full covariance model, or when using a covariance function, right, like an exponential or Matern covariance function where you only have 2 or 3 parameters. It's somewhere in the middle, and Monte Carlo procedures and rapidity of convergence and things like that from probability, but still it's certainly worthwhile looking at. So I think I'll stop here and acknowledge my co-authors and others who have given me slides.